Help me keep the flames. Let me hear your ways. Guiding on it. 'Cause you're the only friend who can set my
This is Joanne Jenkins, CEO of AARP. The coronavirus continues to affect us all, and we are here actively supporting you and your. Good morning, everyone. I think we'll start shortly. I think right now it's 7:56. So I think I did have some time and did some video. This is last spring that I went up to South Dakota and then go around to the Great Plain, northern part of Colorado, and spend a week there in middle of nowhere and observing the great sage grouse. So I think we have 2 or 3 minutes before we start, so I'll play this for you all. Okay. Let me just. I think I had to switch the screen, so I have to go to the scene. Well, I think it's in at perfect time. So this some of video clip and still image that every trip when I made or I have made, I enjoy the wilderness or the nature. I think that's part of my meditation. But anyhow, let's get started. Good morning, everyone. So I think I mean today is April 21st. As I start every time, I like to start with some reminder. So I mean, let me start with this reminder first. So let me pop up. I mean, to get the full screen. The quick reminder that there is a short assignment. If some of you guys, I think most of you guys already picked the term paper presentation. Some of you guys have not picked, please contact me. There are suggested lists that I already post on the website. And then once you pick the topic, then you can start doing your own research and at least come up with 5 references, the sources that you have or you're going to read in order to study and then summarize and then make the presentation. Okay, so the presentation, term paper presentation, the due date is on April 28th. Okay, so the reference is due on April 25th. Some of you guys already send or upload the 5 references, which I think I'm very proud of you guys. Okay, and some of you guys may already have some. Go ahead and post. You don't have to wait for the deadline. The reference can be changed. Okay, I think the reason why I'm asking you to post 5 reference in a way to help you to manage your time. Okay, so if you guys have not done that, then you should start and then upload the reference by Friday, and then you can have the weekend to work on the presentation. Okay, which is the due date on April 28th. The expectation is that you're gonna have the PowerPoint or PDF presentation ready and upload to the Moodle, as well as when I schedule your turn. It's gonna be Zoom session that I gonna allow you to share screen, and then you can make presentation. And then while you make presentation during the whole session, I gonna record the video and later on upload to the our upload to YouTube, and later on create the link from Moodle and point to that. If future quizzes, it will be based upon this presentation also. So I would require everyone to, if you guys, if it's not your turn and you can be there, then I would ask you to review those presentation or your peer presentation. All right, and then last but not least, reminder is the dining philosopher programming assignment. As I told you, we're gonna have the whole entire quarter 2 programming assignments. Okay, the first one I already posted long time ago about the tech shell. So I'm hoping that some of you guys, continue from whatever your previous 220, or for someone who has not done that yet, and with maybe Ibrahim or other instructor. I think I already upload some whatever kickstart code so that you can use those. Okay, and the dining philosopher is also another programming assignment that I plan for. Multiple objective for these dining philosophers. Okay, one of which is, as I mentioned in the class, that multitasking or multi-thread programming is quite important for now on and future whatever career, if you're gonna be in a software development industry. Okay, because as I mentioned that most of the current CPU or hardware, they are multi-cores. So multi-thread is very appropriate or suitable for multi-core type of architecture, because it's allow you to spawn off many subtasks and then create a multiple concurrent kind of unit of execution called thread, which is we call lightweight process. Okay, so the one of the main objective for you to acquire knowledge or hand-on experience on p-thread or multi-thread programming. Secondly, also I like you to be aware of deadlock or mutual exclusion that could lead to deadlock. So in that case, in your dining philosopher problem, you should handle to prevent the deadlock. I will continue on and cover chapter 6 first, which is synchronization. Okay, and then chapter 7 is the deadlock. It may be a little kind of backward because we already touched upon synchronization and deadlock during we talk about p-thread. Okay, I think those I can't avoid because one of which main feature in p-thread, beside create thread and then joining thread, but also synchronization is equally important, because to write a correct program, the data or the result that you produce must be correct and also consistent. It's not like, one time exactly the same code, it produce one value, another time produce another value. Okay, even though exactly the same data or the same logic, that's not acceptable. That means the output would be incorrect or inconsistency, which it would be very difficult to troubleshooting. Okay, so therefore any code segment that you share common data or common resource that two or more thread or processes try to access, especially both would update those shared variable. Those segment of code called critical section that you must ensure we call synchronization. Okay, p-thread support simple construct call or syntax called mutex lock and unlock. Okay, so during after I finish chapter 6, which is synchronization, I may pause before continue on to chapter 7, which is deadlock. I would talk a little more on the dining philosopher problem. I mean, specifically go into detail and then give you some head start in terms of some ideas, some snippet of code, how to incorporate into your program. Okay, and then uh, describe a little more logic, okay, in which how to handle the deadlock. Okay, so good morning everyone again. I just keep, if you see me keep looking to the left hand side, that's my iPad that I have our live broadcast screen there from YouTube. And whatever your type, if you have any question in the live chat channel, I would be able to see from there. Okay, because my main screen that in front of me is just full screen that I would not see the YouTube view. Okay, all right, let's get started, guys. Any question, please feel free to type on the live chat. All right. Also, I'd like to acknowledge some of you guys who has contacted me, and we done some Zoom session. I mean, from end of last week and also during the weekend, because that person has some doubt or some question about the homework. So I think, as I told you, it doesn't have to be during my office hour. If you want to talk to me on certain time, you can send me email, but just give me a few hours lead time, because sometimes I don't sit in front of computer all the time. So I wander around in my house, cleaning up my house, do different other things. Okay, so but then once I read your email, I would respond immediately, and then we can get on. So I think I have a good time talking to one of your friends there, that not only asking question about the homework, but also I got some feedback about this live broadcast, because as I mentioned to you before, this online teaching is also new to us too. I'm learning as well as you are learning toward this online or distance learning. I hope that I think it worked, and I think you have some sort of a good learning experience, even though, I think our preferred mode would be face to face. So let's talk about chapter 6, which is process or thread synchronization. This is outline that we gonna touch upon. Okay, talk about the background, and then continue talking about different problem with respect to synchronization. Okay, I probably would not cover everything because some of those synchronization mechanism is not being used in the current time. Okay, like monitor or some sort of later on some algorithm. Okay, so I will stop at some point. So let's get started. Okay, we're gonna go through some of these topic in detail. Okay, all right. So I think motivation on synchronization with multi-programming or multitasking, that most computing environment, you're gonna see that there are many programs simultaneously working, and some of them may communicate. Some program in fact is multitasking in the sense that it implement multi-thread. Some modern, just like if you guys use Adobe, um, um, whatever, Photoshop or Lightroom. Okay, some of those I believe that if if your hardware is multi-core, even GPU, it will be aware of those hardware and then take advantage by that program would spawn multiple thread and then running on those hardware, okay, specific hardware, so that it gets some speed up, okay. So multi-programming or multitasking become a common programming paradigm, okay, especially for multi-core type of architecture, okay. But then all these tasks are communicating, okay. So some tasks may be act as producer, some tasks may be act as consumer, or maybe you may have multiple producer and multiple consumer that communicate among each others, okay. So it could come to what many apps, okay, that you start, and then some of those apps may share common data, spreadsheet or file or whatnot, okay. um, as I mentioned, okay, all these multi-programming or multitasking could be multiple processes where you start same app or different app multiple time, okay, in order to reduce the computation time or the result that the time that to produce those results. But then we also touch upon the concept of thread, which we call lightweight process, okay. It's more efficient than multiple processes. I mean, for example, if you would like to process, large image, okay, you may have one image processing application that run, okay, but then one application, one instance, which is run on traditional single thread on single process, okay, it may take 5 hours to complete that type of image analysis, okay. What if you want to reduce time in half? In that case, you may start 2 copies, okay. If you want to reduce further down, then you may start application into 3, 4, 5, 6 copies, okay, where each copy will handle a portion of the data, so then you can speed up. But as I mentioned to you, when you have multiple instance of those processes, okay, start, then each process has its own memory footprint. So therefore, it's going to have a duplication of the same executable, the data, but except maybe you have an index or an ID associated with each of those processes, okay? However, in terms of thread multi-threading, all threads share the same common code, share common data. So therefore, the startup time is faster, less overhead, and also it runs faster because switching between all those thread communication is also quite easy because all multiple thread can read and write to the shared memory as if a local a share variables, okay, among those threads, okay. But then once you have multiple threads to access the same shared data, care must be taken. Why? Because the data may be produced or the result may be produced inconsistently. Okay. Last time I demonstrate the segment of program called count plus plus, having 2 threads to execute. One time you may have the result 2, another time maybe 3. Okay. But then if everything correct, then it should produce the same result every time. Okay. So I think that's what we talked about, multi-thread last time. About p-thread specifically talk about mutex, which is a short name of mutual exclusion, that we have 2 construct or 2 syntax that we normally use to encapsulate critical section. One we call mutex lock, or p-thread, the full name is p-thread mutex lock, okay, and then it will enter the critical section where that section one thread will be able to enter one at a time. Once the thread is complete within that critical section, then it will call pthread mutex unlock. Just like you have a share room and then one person can enter that room, okay, which is good. That if you program correctly, okay, then it will ensure that no 2 processes try to compete and update the same share variable in a way that it will cause we call racing condition. Okay. I also gonna touch upon later on, because these mutex or mutual exclusion or synchronization could also lead to deadlock situation, where deadlock situation you can feel like your program is hang forever, it would not proceed to the next, because in the case that when you lock before you enter critical section, what happens if you forget to unlock, or what happened for the process to enter that critical section and it happened to die before it will be able to unlock. So in that case, no other thread or process could enter that critical section. Therefore, the whole system may host up. Okay, so that's, I think you have to be careful. Every tools, every mechanism, there would be plus and minus or pros and cons. Okay, so I think Jake has asked the question. Okay, let me just pause. Okay, the question that Jake asked: one of my teacher does not even upload when talking or teaching, just book work, exam. So it's nice to actually hear from them like you are doing. Well, I think I'll provide this input to our meeting. Right now, every week, all professor in computer science and computer engineer, we gather through Zoom, and then everyone would provide their input, their opinion, their needs, their plus and minus. Explain that they're teaching you, because I think as I mentioned to some of you guys, this is difficult time, so I think everyone are adjusting. For example, the activities such as the test or the quiz, I used to have only 2. Now I plan to have 6 to 10, and then describe or translate my quiz into the web form. It takes 5 to 10 times more work than I used to do. So thanks, Jake, for your input. So we'll provide to our faculty meeting. But now let's come back to look into the synchronization. In case that when you have a programming paradigm where you have producer and consumer, okay, sometimes if you have one data element, okay, then you have to ensure that the faster processing or thread would not override whatever those data item before the consumer can read it. Okay, so therefore, for sure, synchronization is really a must. Okay, when you have this producer and consumer, but sometimes they may try to relax if you if you perform block read and write. That means every time when a process try to enter or update the data, another process has to be blocked. Okay, in that case, it may not be as efficient. So therefore, there's some paradigm where people has introduced n number of item for the buffer. So in case that one process may be faster or slower than the other, it will not block the progress from the other one by using this buffer. Okay, why one keep writing it and then another one keep reading it, and then you use number of item here to be the mitigation in a way that if one faster than the other. But then also we may run into an issue that this number of item in the buffer is limited. Okay, what if one is super fast? Okay, so therefore the consumer may not be able to read when this guy just keep running behind and then reach to the point. So once the buffer is full, meaning that if there are some item that has not been read, and then there are no more free buffer that the producer can produce, then in that case you have to use synchronization mechanism to ensure that when the buffer is full, you have stop. Okay, and then in some situation you may have even more difficult or more complex, where you have multiple producer and multiple consumer. Okay, this also could be quite complex in terms of programming, but it's doable. Okay, as long as you know what you're doing, as long as you can visualize and come up or design the logic in a way that you would ensure a good consistency in terms of synchronization, but not lead to the deadlock situation that we talk later on. Okay, so let's get into a little more detail. This is just some motivation showing you. In fact, this is the real in the real world. In your previous classes when you study, okay, normally you have only one process, and that process would start from beginning of your main program function and then sequentially work on all the way to the end. But then the current or the new type of application, I would say that, you know, if you want to make your application to be killer app, the app that would run very fast but also work well, then you need to adopt, I mean, the concept of parallel programming or multi-threading. So therefore, some of the paradigm that I show you, like multiple producer consumer kind of situation, is not going to be, I think it would be easily, you know, I mean, can be easily seen or be introduced, you know, in current situation or in near future. Now let's take a look at little more kind of descriptive background. Okay, I think I already give you some pictorial idea or picture in terms of mental picture on multitasking. Okay, so multitasking then it would lead to concurrent access on shared data. Sometimes some situation, okay, you have multiple producer, multiple consumer, it try to access the same share variable or global variable. Therefore, it may result in data inconsistency, as I mentioned. So maintain data consistency, okay, is a very critical, okay. It requires a certain mechanism we call synchronization mechanism to ensure an orderly execution of these cooperating processes, okay. As I mentioned to you before, okay, if we don't be careful, the data inconsistency may happen just like this picture that I pop on the right hand side. I already showed you last time, okay, when I demonstrate synchronization issue or multi-thread try to access the same global variable called count, okay, where you may have two threads to execute count plus plus, okay, then each thread has its own set of register. So therefore this count plus plus high level C++ language, okay, may translate into multiple machine instructions, just like 1 2 3 here, and then this sequence of machine instruction from each thread may be interleaved execution. So therefore it may create a data inconsistency, okay, as I demonstrated last time to you. If we initialize count equal to 0, if we have thread 1 and thread 2 execute count plus plus, then, you know, if to have the correct answer, it should produce the value 2 after thread 1 and thread 2 execute. But as I demonstrate this one possibility, okay, the result end up as 1, okay, so which is wrong. Therefore, I mean, for this share variable, for example, the count plus plus, we have to make it as critical section where we will perform synchronization by regulate or ensure orderly execution in the right way, so that all these critical section will be executed one at a time by each process, okay, or each thread. So in that case, you know, I mean, suppose we want to provide the solution for producer and consumer to fill all the buffer. Let's say that we have situation where we have producer and consumer, and producer and consumer would read and write or write and read, okay, share the data, but instead of a one common variable or integer, we create a buffer, okay, where we define count as a number or count as an item that being tracked, okay, whether the buffer full or buffer empty, okay. So we can initialize count as 0, okay, and then we can start increment the producer, okay. Whenever producer update the item there, then we add 1, okay, to the count, okay. Once the consumer read that item from the buffer, then we decrement count by 1. So therefore, count is a global variable, and if it must be accessed by two processes or two threads, okay, then therefore we must ensure that this count has to be encapsulated with mutual exclusion or synchronization. Um, so just like this picture, okay. Now let me, I think there are two, let me just show you a first example first, okay, in terms of bounded buffer, producer and consumer, okay. We we'll later on talk about the synchronization, but let generally look into the concept how this thing work. Okay, so on the left hand side we have the code for producer. Okay, where we declare next produced item as item. Okay, which is item is and this array is an array of item. Okay, where the producer will write something to this item, okay, and then producer use in as an index, okay, that indicate the current item that the producer is writing to the buffer, okay, and then out is an index that the consumer read that item out, okay. So in that case, producer and consumer can work in parallel, okay, where the producer all it has to keep track is the in, okay, which is the in index, but also it also have to check, okay, whether the in is start hitting or running, I mean into the out, okay, which mean the producer is much faster that it try to keep running, okay, and overrun the consumer item that the consumer has to read that item. So therefore we have to have a guard, okay, or a logic in a way that, hey, if it start if it about to overrun, okay, then we're gonna have to make producer wait, okay. Meanwhile the consumer, if consumer is very fast and it keep reading, okay, until the out equal to in, that means there's no more unread item, okay, that consumer has read, okay, therefore we're gonna have to stop consumer, okay. So let's come and analyze quickly this logic, okay. We assume that the producer will be in this infinite loop. All he does is keep producing, okay, and then the first statement within the forever in infinite loop, okay, we check, okay, while in plus one, that means the next index, the next producer index or write index, okay, input index, okay, mod buffer side. If you know these operators, okay, is modular arithmetic. That means it's circular kind of queue. If it's I think if it divides by that buffer side, then if it falls out from the buffer or the index of the buffer, then it will go back and round back to the beginning of the buffer index again, okay. Then we'll check if it equal to out. That means if in about to run over the out index, which is consumer index, then we do busy waiting, okay. Here you can see that this is why we do nothing. That means we just keep spinning. We in this case the producer will keep checking until this statement is not true, until this statement saying that P producer will not overrun consumer, then it's gonna go to the next line, okay, which is found out from this loop, okay, and then call buffer in equal to next producer. That means there are already a free item that the producer can produce the next item into the buffer, and then it will update in equal to in plus one mod buffer size, okay. So I think this is quite obvious. Are you guys with me so far? You not follow, please type, okay. It's not that hard. Now meanwhile the consumer all he does is just keep reading, okay. So it will check whether if y in equal to out. The reason why you don't have to do the mod something, you know, like percent sign and then the buffer size, because it's being taken care by this, the out being taken care by this. So all we have to do is just check if in equal to out, and then in this case the consumer will not touch the in value at all, okay. All he does is just update the out, because the out is an index for consumer, okay, that would point to the current rate item, okay. So in that case, it will check if in equal to out, that means the buffer is empty, okay. So therefore it do nothing, okay. Otherwise it gonna start reading, okay, the current rate buffer assigned to next consumer, and then it will update out equal to out plus one, okay, mod buffer size, okay. So this logic, okay, it will ensure that producer and consumer will not overrun. Granted that some of these operation, when you are doing the update here, okay, or when you do this update, it must be synchronized, okay, because otherwise some of these high level instruction, it may be translated into low level machine instruction, so that the machine instruction may be overlapped, okay. So let me grab my warm water to lubricate my throat. Sorry, guys. Or an alternatively, okay, maybe obvious. Let me just show you an alternative solution similar to producer and consumer code, okay. So now we track with number called count, okay. We do count plus plus or count minus plus plus for the producer, or count minus minus, okay. So I think in this case it look more obvious that this count, okay, which is a global variable, and if we don't protect, meaning that each of the process, like producer, consumer, when I call process, similar to thread, each of thread, okay, if each of these process or thread, okay, trying to access the same share variable, okay, then in this case, if we don't protect these two share variable, which is both processee or thread can access simultaneously, then the result can be inconsistent, okay. So therefore, obviously, when you start writing a parallel or multitasking or parallel programming, that each of those parallel execution try to access the same share variable, you must identify which part of your code is critical section, okay, meaning that you have to wrap around or make this operation to be synchronized operation. For example, if you use pthread, it's gonna be pthread mutex lock and unlock, okay. All right, so are you guys with me? I think my motivation to show you that, perhaps in the future, when you start writing multitasking, okay, then upon your thread or your process, you try to update or share the same variables, then you need to identify the critical section or segment of code that you have to encapsulate with mutex lock and unlock, because otherwise the result may be inconsistency. And someone may say that, why don't we just wrap around the whole thing as synchronized critical section, where we have mutex lock and unlock here? Well, I mean, sometimes if the logic permit you to do so, it may work. But then why would you want to do that? The more you put synchronization there, the slowdown or the performance will get suffer. Why? Because, I mean, assuming that if you have two processes or two thread running, okay, then it can alternate, one or the other will access that critical section. But what if you have 16 threads? Then when one thread access critical section, all 15 threads we have to wait. So why would you spawn 16 thread where every time you have one process to execute? So therefore, synchronization is important, but also you should be mindful. Don't use it sparingly, or you don't use it anytime you want. Like casually. You have to be careful that you should use in the code section that it's critical in order to wrap around and make sure that it produce consistency result. Okay, that's what leading to racing condition. I think we already touched upon this, but let's take a look at it again, okay? Assuming that you have a operation called count plus plus, at high level in C++, okay? Those can be translated into maybe perhaps 3 machine code, where at first you assign the value of count to register 1, which is in thread number 1. And then count plus plus perform register 1 plus 1, assign the result back to that register, and then you load back that register to that count. Someone may ask, why would you want to do this way? Well, we have no choice, because as you know that when you load the data, okay, let's say when you initialize your program, you may read your data from maybe the network or user input, or maybe from the hard drive, okay, or from a file. And then you store in the variable which is in your main memory, okay. Then if you visualize how your computer works, okay, you have CPU, you have main memory, or those SIM or memory plugged into the same motherboard, but they are not in the same unit, okay. Therefore, in order for CPU to compute something, it must load the data from the memory, okay. And then there is some local storage in CPU. In fact, in between there may be cache, okay, which is not register. Register are a local storage to CPU that sit in the same CPU next to CPU, where you can load the data from memory or cache into register. And then normally all your operation would perform on that register. And once the register get the new result, then you want to store back into your variable, then you load from register back to the memory. So simple instruction like this could be broken down into multiple low-level instruction like machine code, okay. So therefore you must be very careful. That's why many times someone may ask me a question that, why do I need to study operating system? I will never be a developer or write new operating system. But in fact, understand this phenomenon where the high-level programming language could translate into the machine code, and then operating system is sit in between, it handle this activity. It gives you an ability to understand the low-level thing in order to prevent, some issue or some problem. When you compare yourself with someone, who never study computer science or in-depth operating system or runtime, I think they cannot visualize or understand how the problem could happen, okay? But I think in this case, I hope you start seeing the benefit of why do we study this operating system and get into more detail. Now, from producer and consumer, as I showed from previous slide, producer trying to do count plus plus in order for producer to track whether the buffer is full or not. Meanwhile, the consumer, once it read the item, then it perform count minus minus, okay. So count minus minus high level C++ can be translated into similar 3 instruction, machine code instruction, where you start loading value of count to register, which could be different register than different thread, right? We call, let's say, register 2. And then when it try to perform count minus minus, then you do register 2 minus 1, and then assign the result back to register 2. Here you may have the machine code instruction called DEC, decrement. I have seen in the past when I have written like 30 years ago when I was in undergraduate or postgraduate, okay. And in here, I think I remember there's instruction called INC, which is increment machine code that you can increment the register. So you say INC R1, okay, or DEC R2. This is a potential machine instruction code that you either increment or decrement, which is similar to this logic. Okay, and then after you decrement from register 2, then you load the result back to count. Okay, now if you take a look at the timeline, where producer and consumer may execute count plus plus and count minus minus. Okay, at T0, producer may execute register equal to count. Let's say that initially count equal to 5, okay. Then producer may continue execute register equal to register plus 1. Therefore, register 1 is equal to 6 now, okay. And then let's say that the runtime schedule thread number 2 or consumer to execute, then it execute two more instruction that start load the count value of count to register 2, but this register one has not load the value 6 back to count yet. So therefore, register 2 will get the previous value of count, which is 5. Okay, and then it will perform count minus minus. Okay, so register 2 equal to register 2 plus minus 1. Then now from value 5 down to 4. Okay, then at time t4, producer thread or process would load value of register 1 back to count, and then T5 load the value of register 1 back to count. So here you get the result as 4, okay, which is incorrect. Okay, you're supposed to, if both execute, both thread execute correctly, the count should remain to be 5 because one try to decrement by 1, another one try to increment by 1. Okay, but then here you get result 4, which is incorrect. Okay, did you see that? So therefore, as I mentioned that this the variable count, that whenever we apply any operation, if it's share variable or global variable for this multi-thread, okay, then it will be considered as a critical section. So therefore, you have to wrap around the synchronization or mutex type of operation. Make sense, guys? Okay, let's move on. Now, the solution to critical section problem is, I think there are 3 elements in order to ensure a correct critical section solution to critical section. Okay, first you have to have a mutual exclusion. When we say mutual exclusion, for example, the operations such as pthread underscore mutex lock and unlock, those we call mutual exclusion or synchronization. All these are synonym, okay, or the same meaning. We say that the mutual exclusion defined as if process pi is executing in the critical section, okay, then no other process or thread can be executed in that critical section. Okay, that means critical section, one process or thread can execution one at the time. Okay, that's we call mutual exclusion. Only mutual exclusion may not be a correct solution, total correct solution. It also have to ensure progress. Okay, that means if no process is executing in its critical section, and there exists some processes that wish to enter their critical section, okay, then the selection of the processes that will enter the critical section cannot be postponed indefinitely. That means the progress must be ensured. There should not be starvation where one process will stop at waiting state all the time. Okay, so therefore, not only mutual exclusion, okay, must be ensured in order to have a good solution for critical section problem, but also you have to ensure progress as well. Third, okay, we call bounded waiting. Okay, a bound must exist on the number of times that other processes are allowed to enter their critical section. Okay, after a process has made a request to enter its critical section before the request is granted. Okay, so assuming that there are assume that each process must execute at non-zero speed. No assumption concerning relative speed of end processing. So what it's trying to say, the bounded waiting, that means if one process waiting, okay, to enter critical section, it must be the waiting time must be bounded. So in that case, you can apply the aging. Okay, remember, guys, when we talk about scheduling algorithm in chapter 5, for example, the shortest job first or different other priority scheduling. Sometimes priority scheduling is good, but it could lead to indefinite, okay, waiting. Okay, so therefore, the progress must be wait, and also you need to make sure that, the waiting time is being bound up to some number. Okay, so therefore some algorithm you can use to apply this. For example, the promotion or demotion, in order to improve the chance of the less fortunate process by using aging algorithm. Okay, as such. So for this quick conclusion, I mean, to have the correct solution or good solution for critical section problem, okay, is that first we must ensure mutual exclusion. Second, okay, we also must maintain the progress, which means if process wish to enter, that process will not wait forever. And last but not least, the wait time must be bounded wait time. Okay, so these are three criteria in order to have a good solution for critical section. Now, I think Peterson's solution is a classic solution, okay, that has been introduced at least, I would say, 25 to 30 years. I remember when I was in my study post undergraduate, okay, before enter graduate school, I studied advanced operating system. Okay, I think I already have seen this solution. In fact, in order to ensure the critical section, because it has to update the count, okay, or the flag in order to ensure the orderly execution, as well as the to prevent the deadlock, and also to perform synchronization. So in this case, Peterson's solution introduced or proposed a solution that the load and the store instruction must be atomic, okay, which is critical section. The atomic meaning that one process or one thread can execute that instruction one at a time, and that cannot be interrupted. Okay, so in this case, Peterson, okay, has introduced two shared variable called turn and flag. Okay, where each the variable turn will indicate that whose turn is supposed to enter the critical section, and the flag, okay, is used to indicate that if that process, okay, is ready to enter the critical section, when the flag I, that means the process I, okay, equal to true, that process is ready to enter critical section. Okay, so let's take a look at the algorithm that Peterson has introduced, and this is a generic kind of critical section that Peterson introduced, and that mean it could be n number of processes. That's why you see that he defined P as processor and sub I, where I could be 0 to n number. Okay, now in his algorithm, okay, he demonstrated by using flag and turn in order to encapsulate critical section. By the way, this is just a primitive or low level type of implementation. In fact, I mean, the whole thing can be implemented as mutex lock. Okay, I believe that, I mean, the current implementation of those critical section or the mutual exclusion like mutex lock and unlock, okay, could implement such as the whole segment there. Okay, and then you have mutex unlock here. So when I was young, I studied this detail, how the lock can be implemented, okay, using flag or turn, so that we can ensure this as critical section, and then the unlock would be otherwise. So in here it set the flag I equal to true. That means process I is ready, okay, as initial, okay, and then process I would assign turn equal to J. That means he politely to say, hey, J, you can use this turn first, okay? And then the process I will check that if flag J and turn equal to J, okay? He do nothing. That means if J is ready and then the flag turn, flag of J turn to be true, that means J is about enter critical section, and therefore process I would do busy waiting, meaning that do nothing, keep busy waiting in this loop until this condition is false. One is false, that means I is ready. Then he will enter the critical section, and then after he finish, then he turn the flag false, and then continue execute the remainder of the section. So this is a general idea about the critical section, the solution that Peterson has introduced a classic low level how to use flag and turn. And by the way, the flag and turn is much used the load and store instruction, which is atomic, in order to ensure that this is going to be correct solution. Okay, so it's not that difficult. I would say that if you guys kind of follow me, you should be able to start thinking about this logic and figure it out. In fact, I think the key thing is just use two variable. One is flag variable, another one is true turn variable. And then if flag that represent its own flag to that process I, it become true, then it will start execute. So that means here process I or PI declare that he's ready, but then he provide turn to others first, and now I mean he'll check whether the other guy flag, okay, which is if it's true, and then the turn is J, meaning that his partner is ready, equal to J, then he would do nothing. Okay, we call spinning, just do nothing here. Okay, waiting until the other guy set flag equal to false, meaning that the flag J will be equal to false after the process J execute critical section, and therefore this condition would be false, and then he gonna enter this one. Okay, make sense? Let me see what's gonna be next, because right now it's about the halftime break. Okay, why don't we do this, guys? Let's take maybe 3 minute breaks. Okay, right now is 8:52. Let's take a 3 minute break around 8:55. Okay, we'll be back and resume this discussion, because I think this is the good point that we're gonna stop at synchronization hardware. Okay, and then we're gonna continue on and complete this lecture or chapter 6. Okay, all right, guys. So I think we'll be back in 3 minutes.
Our community. Every day, we're providing trusted information from top health experts, sharing tools to help protect families from fraud, and creating resources to support family caregivers everywhere. As always, you can count on AARP to advocate for you and your family. Join us and stay connected at aarp.org/coronavirus.
When the land is your livelihood, there are no shortcuts. Doing it right is plan A and plan B. Because there's no time for downtime. You need equipment that has your back, that's built to the same high standards you live by, that's up to the challenge. Half-ton hay bale challenges, runaway cattle challenges, that's a lot of mulch challenges. You need the power, durability, and versatility of Kubota equipment. Built right to get every job done right. Kubota. Together we do more.
take me to the mountain. You take me to the depths. You take me to the fountain. When I have nothing left. You lift my head. You lift my head. You lift my head. You lift my head. You are all I need. You are strength, never failing. You are all I see. You alone are enough. In you I live, in you I'll stay. By your word, like the rain. You take me to the mountain. You take me to the depths. You take me to the fountain. I have nothing left. You lift my head. You lift my head. You. Alright, guys. So let's resume our discussion on the synchronization. Most synchronization, I think, is support in collaboration between hardware and operating system. Okay, so operating system by itself, it could provide synchronization, but without hardware support, the synchronization would be very inefficient, okay, because it has to check, it has to monitor, it has to start and stop, do a lot of low level things. So therefore it's gonna impose a lot of overhead. So therefore I think this is not new, it's long time ago, even though a unit processor or CPU with single core, okay, the synchronization or multitasking is support long before the multi-core type of situation, okay, because sometimes, as you know, that when you have one process that try to access IO, then CPU become available. Why not just switch to have another process execute on CPU, okay? But then once that process coming back, and then maybe two or more process try to access the same share variable, even though on unit processors, okay, or unique or single core CPU, the synchronization must be ensured. So in case for unique processor, we can operating system could simply use interrupt, okay, or could disable interrupt in order to ensure the code, the current running code would execute without preemption. In general, it would be inefficient, as I told you, okay, on especially on multi-core type of architecture. So therefore, the modern CPU or multi-core provide a special atomic hardware instruction, okay, where when we say atomic, okay, let me just circle the word atomic here. That means that operation can be executed one at a time. There is no other process or thread can execute that atomic operation. Example of those atomic hardware instructions, such as a test and set value, or swapping the content of two memory words, okay? So those could be executed in one instruction clock cycle. That means it just requires one more hardware instruction, which is quite quick, okay? So therefore, you know, with hardware support instruction like test and set or swap content of two memory words, okay? It could be used to implement the synchronization operation, okay?
for example, how to use test and set in order to provide lock and unlock. Here we have the test and set, okay, on that lock, which is a special variable, okay. So that means one process or one thread can execute one at a time. If that lock is true, okay, that means that process will have to wait. If it fall, then it will fall through. As you see that here, the blocking operation that being used in this implementation, it used a we call spin lock. That means do nothing. The spin, there are two ways in order to implement this block or lock and unlock. One is simply used we call spin lock, SPIN, or another word we call BC looping, okay. For critical section that very small, this spin lock may be more useful or less overhead than an alternative solution by using operating system to suspend the process, just like those process scheduling. Because you guys remember, if we want to suspend a process in CPU scheduling, we have to perform context switching by saving process status into PCB and then reload something. So in that case, it critical section is very small, or maybe just one instruction there. Spinning lock, meaning that just spinning, do nothing. It may be cheaper implementation and easier to implement than just suspend a process, okay. So I think later on we're going to talk about how to implement block and unblock, okay. But I think in this case, two birds in one shot, we just demonstrate how to use test and set as atomic operation in order to implement the lock and unlock, okay. And here we'll just check, and if it's false, then it can continue on. But if it's true, that means one already enter the lock, then it just spin lock here or do nothing, okay. Otherwise it start execute the critical section and then reset lock to be false and then execute the remainder. So this is low level. I mean, for a typical programmer, if you are just like P-thread programmers, okay, you don't have to care about this. Here we just show you the low level, how those lock and unlock get implemented, okay. Another important concept or classic synchronization tool called semaphore, okay, which has operation P or V or similar to wait and signal, okay. Wait is mean like lock, and then signal is unlock similarly, okay. Lock, unlock concept just like kind of similar, but I think they use slightly different terminology. Originally, the semaphore has been introduced more than 30 years ago. It original operation called P, which is similar to wait, and V is similar to signal, okay. In order to use semaphore, okay, then you have to declare a special variable, some semaphore called S, okay. Then you call wait S, okay, where you're gonna check if S is less than or equal to 0, okay. Then it get blocked or do nothing. Okay, so semaphore is a special integer variable. If it's greater than 0, then it's gonna continue on and start enter the critical section, okay. So if it less than or equal to 0, it's gonna wait, and then otherwise, okay, it's going to do S minus minus. That means it will try to enter the critical section and then update the S value, okay. Meanwhile, if it's complete the critical section, then it's going to call signal S, okay. So once, I mean, you can think about wait just before critical section, and then you provide signal at the end of critical section. Then S, all it does, it's gonna do S plus plus. That means it's gonna update the value S. So in this case, the main, the crux of this logic is the value of S, okay. If it's greater than 0, then it's gonna fall through and enter critical section. Otherwise, it will wait, okay? And in this case, the wait implement by using spin lock or busy looping, okay, which is very quick. But as I think I mentioned, there's an alternative solution. Instead of you perform busy waiting, you can block or suspend the process, just like that context switching, put the process into sleep state, okay, until it's ready to come back and execute, then it will be wake up. All right, so I think this is an idea of semaphore. We're gonna talk and then show you sample code how semaphore work a little later on, okay. Now, as I mentioned, okay, semaphore is a classic or general synchronization tools, okay, similar to mutex lock and unlock. There are two solution or alternative solution to semaphore. One we call counting semaphore, another one called binary semaphore. Counting semaphore, in fact, it use integer value, can be an over range of unrestricted domain, okay. That means you can have many or more um, process try to enter, so therefore you're going to use this count in order to track how many has been in waiting, okay, and how, and then because obviously you have only one that can execute, okay. But by the way, binary semaphore is just like 0 or 1, enter or not enter, lock and unlock. So in fact, the binary semaphore you can use to implement counting semaphore, where counting semaphore is provide you a status of the wait queue, okay. um, so in fact, the way to use semaphore, normally you declare semaphore s, which is a spatial variable, and then normally you initialize to be 1, okay. And then your code would have wait and then the semaphore variable. If the weight, okay, is 1 or greater than 0, then it will enter the critical section. Otherwise, the weight will wait until s is greater than 0, okay. After that given process complete critical section and come out, it's gonna call signal, which is similar to unlock. Then the signal, as I show you, is s++, so it will update the value. Whereas wait s, it will decrement s by 1. Once it enter, then it say that I'm gonna lock it, okay, and then enter critical section. So a typical code, if you have producer and consumer here, you're gonna have and then you have critical section, you're gonna have wait and then signal, okay. But sometimes you may have multiple critical sections within that segment of code. So instead of you are using one semaphore, you can use multiple semaphore as well, okay. I'm gonna show you little later in terms of, it's gonna look similar to this. So instead of you have wait s, okay, and then you may have wait q here, where in your critical section you may have 2 or more share variable that you want to protect. So therefore you're going to use each of semaphore to protect the logic, okay, of those local variables, okay. And then once you have wait s and wait q, then you're going to have to say signal q and signal s, which means unlock once you come out from critical section. Does it make sense, guys? Okay. All right, okay. So as I mentioned to you, okay, two way of wait and signal can be implemented, okay. The logic is similar, meaning that if one try to enter critical section, if the value of semaphore is greater than 0, then the process or the thread will enter and decrement the value of that semaphore. Let me just, I'm sorry. Someone just called me, okay, so I just decline those things. So these two implementation with respect to the waiting, okay, or waiting mechanism, because the logic of wait is and signal are similar. Wait is just like before you enter the critical section, you would check the value of semaphore, whether if it's greater than 0 or not. If it's greater than 0, then it will enter, but before it's entered, then it will decrement the value of the semaphore, okay, by 1. So that when another process try to enter call wait again, it's already, let's say that initially you declare as 1, okay, then it's gonna be 0. So the other guy will wait until this guy complete critical section called signal. And then that signal logic is increment the semaphore where you buy 1, okay. Uh, um, so in that case, from 0 go back to 1, and the other guy now was checking, okay, to see whether the s is greater than 0. If once s is greater than 0, then he can enter, okay. Now when we look into how wait implement blocking or waiting, okay, you could simply implement busy waiting in critical section. In terms of when we do busy waiting, when you have while loop, if you do nothing, meaning that nothing, and then you have semicolon in your C instruction, okay, this implementation is just very simple, short, but it just chill, but it still remain on the CPU, execute and check it all the time, okay. So if your critical section is small, okay, then it doesn't matter, it may be worth it than you put the process to sleep, okay. Otherwise, if your critical section is very substantial or significant, it has a big loop and all those, maybe it may be better idea to use an alternative blocking solution by use process scheduling to suspend the process, okay. Does it make sense to you guys? So I think two school of thought, okay, in terms of once you lock the process has to wait whether you're gonna do busy waiting or you're gonna use process scheduling. But using process scheduling, your critical section must be significant, okay. And by the way, if you use some of the tools like pthread, you have no choice which one you're gonna use, okay. I think now we talk about if you were an implementer of pthread, trying to make sure you provide the tool in a way that the programmer can write efficient code. If I were whatever developer of pthread, I may provide two type of wait or signal. One I would call wait. Keep. I have a lot of this spam call all the time. I don't know why. So I think this is a general idea on how semaphore get implemented with respect to blocking or lock. Okay. If you guys have any questions, please feel free to type, okay, and into this live chat. I'll be happy to answer your question, okay. And here is the pseudo code how wait and signal get implemented, okay. Here is implement alternative solution instead of busy spinning. So you add the process that wait into waiting queue and then block, okay. And then for signal, okay, you do oppositely by remove process from the waiting queue and then waking up the process, okay. So in that case, it requires extra overhead. But then if your critical section is quite large, it may be worth it, okay. Why? Because in your busy waiting, the process will just keep chewing the CPU. That means it will occupy in a tight loop or spin loop, checking whether S is less than or equal to 0 or not. If not, then spinning, okay. That is only good when you have a small critical section, okay. If you have large critical section, perhaps this process scheduling or context switching process to waiting queue, it may be worth it. Make sense, guys? I think I just want to give you distinction between two alternative solutions, okay. I have a few more slides left in this chapter, and then I'm gonna go to the new assignment that I just post in terms of programming assignment, okay. Now, as I mentioned to you, synchronization may lead to the deadlock. If you lock something but forgot to unlock, or you somehow put the code in a way that it will interlock each other, okay, that could lead to the deadlock. So deadlock situation is undesired situation. It happens when two or more processes are waiting indefinitely for an event to occur, okay, that can caused by another process that waiting, okay. Let's take a look at this simple example, okay. Let's assume that we have P0 and P1, where P0 and P1 try to access this critical section. So let's say that this dot dot is critical section code, okay? And then we declare two semaphore S and Q, where S and Q initially equal to 1, okay? Remember, if semaphore is greater than 0, then the process, once it executes that particular semaphore, then it will proceed to the next statement, okay? Until if the semaphore is equal to or equal or less than 0, then that process will be blocked or waiting, okay? So let's take a look at or analyze this. Let's assume that at time t0, p0 execute wait s. Initially s is equal to 1, right? Then if p0, okay, execute wait s here, then s from 1, okay, will reduce to decrement to 0, and then P1 will proceed to the next line, okay? But let's assume that right before the P1 execute P0 execute wait s, okay? P1 happened to execute wait Q, okay? So Q was previously 1, right? From here, you can see. Now Q once P1 execute wait Q, now Q from 1 becomes 0, okay? All right, okay? So now both S and Q, okay, become 0. Now at time T, let's say this is T0, this is T1. Let's say the time T2, P0 will want to execute wait Q. Now Q is already become 0. So therefore, the P0 gonna get stuck here, will be blocked here, okay? And then that time 3, okay, P1 try to execute because it proceed because of it can grab Q and then continue on. Try to execute wait S, but then S already being 0, right? So then it gonna get stuck here. So in this case, it's gonna cause the deadlock if we don't carefully put wait and signal in the right order, okay, and then lead to a situation we call starvation, okay. So I think you have to be careful. A lot of time, don't casually put wait and signal, and make sure that you put in the correct order in order to ensure that there's no deadlock situation. So in this case, if I ask you a question, normally in some exam or maybe in the homework, I may give you a snippet of code that have a two processing code or this pseudo code, and then have a series of wait and signal, okay, with critical section. The question may be asked to ask you to identify whether these snippets of code would lead to the deadlock or not. If it's so, correct it, okay. So in this case, how would you do here? Okay, in order to not lead to starvation, which is indefinite blocking, okay, here is the solution. Okay, here as I show you, this is deadlock, right? The same code from last page, okay. You have wait S and wait Q here. So both S and Q, first enter, then it's gonna get blocked here, because once P0 try to execute wait Q here, it's already being 0, right? Q being 0, so it get blocked. Likewise, P will also get blocked here because it tried to execute wait here. So the correct solution is that you have to swap, okay, here. Make sure that which one is the semaphore to control first, okay, then swap in the right order. So as you notice that we have wait S and wait Q here, and wait S and wait Q here. So in this case, this is the correct solution. Why? Initially, if this one is both S and Q is 1, let's say that if P0 execute wait S here, okay, then it's gonna continue on, okay. Meanwhile, if P1 try to execute wait S here, it's gonna block up here. It will not be able to enter here. So therefore P1 will continue on and Q still 1. So therefore P0 continue on and then Q becomes 0. Okay, then it will be able to enter this critical section. And then once it's finished, okay, the recommendation when you try to unlock or signal, you do in reverse order of the entry point where you have S and Q here. Then you have Q and S here. Same thing as P1 here, S and Q and S here. And once it finished critical section, then it will call signal by update Q from 0 back to 1, and then signal S update from 0 back to 1, then P1 will be able to enter by call wait S and wait Q, and then enter critical section and then release it. So this is the correct solution. Does it make sense, guys? So I think this is some idea of, showing you, yes, we have a synchronization tool such as semaphore, okay, that you can use in order to make sure that you have a data consistency, but then care must be taken. You must be careful in order to place the right weight and Q, okay, otherwise it may lead to the deadlock. All right, so let's move on. If you guys have any question, feel free to type on, okay. I think I'm look at the question. There's no more question, and we have around 17 people, which is not too bad. Okay, two classic problem of synchronization that people discuss. In fact, in the book, I think one we already talked about is called bounded buffer problem. Okay, when we have the n number of buffer and then we have producer and consumer. Another problem we call dining philosophers, okay, which we're gonna talk or we talk generically, and then we're gonna go and discuss in more detail for our homework, as well as some suggestion or logic. How do you solve the problem? Okay, so I think we already talked about bounded buffer. So let's now talk about dining philosopher problem. The classic dining philosopher problem is defined as n number of 5 number of philosophers that's sitting, okay, on the tables, okay, or around the table, okay, and then each has left and right chopstick, and then in the center there is a rice bowl there. Okay, so in this case we can implement, okay, the logic also saying that the philosopher has to pick both chopstick, left and right hand, in order for he or she can start eating. Okay, so that means the neighboring chopstick are a share variable. Okay, so in that case we can define as a semaphore or the mutex kind of lock and unlock, okay, or the mutex variable. So in this case we can initialize chopstick, okay, an array of 5 chopstick as semaphore, and then all initialize value as 1. Okay, and then we can start perform pick right and left chopstick. However, let's say that if you write the program to implement this situation, and you say that all philosopher, because you can simply write, let's say pthread, and then you can do pthread underscore create, and then assign a function called dining philosopher, and then within that program, if you have simple logic to say within that program or that function, you say that first pick the right, okay, or pick the right and then pick the left, okay, but then you would put mutex lock and unlock or wait and signal. Okay, so in that case everyone gonna pick the right, then where is the left? Because the right one become, which is the left one, okay, to the neighboring, okay, already being picked up. So therefore it's gonna be the deadlock situation. Okay, I think this is example of how this thing get implemented. Then we can say that wait chopstick I, and then wait chopstick I plus 1 mod 5. Okay, so this is number of philosopher, number of chopstick. Okay, and then start eating. But this is deadlock situation. Okay. I think we already talked about this one. Okay, so let me move on and then complete this chapter, and we're gonna talk specifically about the dining philosopher, but then center around P-thread ideas. Okay, which is your programming assignment. Okay, a quick thing before we wrap up these chapters. Okay, in fact, there are synchronization, okay, that provide based on different platform or system. Windows XP has a set of synchronization that you can program multi-thread or multi-programming there. Linux also have its own native synchronization, or Linux or Unix, which is in fact I used to teach synchronization, use low-level semaphore. Okay, in fact, Oracle database, okay, using share variable or message queue as well as this semaphore. So I think in that case, if you are DBA or database administration for Oracle, instruction guide to set up the system. I think first, I think in the past that 20 something years ago, before I moved to Louisiana Tech, I was an engineer, software engineer or architect, solution architect for AT&T, led on Lucent Technology. So we have large database to maintain the subscriber database. Okay, in the past, the installation guide or software is not sophisticated, so it requires us to do some manual configuration. So I think I remember that we have to set up the message queue, the semaphore, and all those. Okay, there's command called IPCS or something. If I'm not IPC something, let me just quickly try to let me do this. Okay. Dash KIPC. You know, if you don't remember thing, you gotta remember, if you know there's some keyword, okay, that you want to find out, then you can use man dash k and then keyword there. Okay, and there's program or libraries, okay, that I'm looking for. In fact, I'm looking for this IPCS. Okay, is reporting system file process communication and facility status. I believe I have to be root or root ROOT. Okay, not just like you are to root. Okay, let me see. I don't think I can execute this one. Let me say IPCS dash L. Okay, yes, I can. Also, I think I'm a staff also, so I can issue the IPCS. Okay, so IPCS is a command on Linux or Unix that you can list inter-process communication, including message queue, semaphore, share memory, and semaphore. As I told you, you know, message queue, you have to have message queue ID. Share memory, you have to have ID. Semaphore is a this synchronization mechanism that you can program low level. Okay, but I think if we have time, I will touch upon this, but I would not see you guys gonna use this a whole lot. But there, in fact, on Linux, there's some native synchronization like semaphore that you can use. Okay, so the command is IPCS. If you are the root, you should be able to issue the command. In fact, you can create your own new semaphore by using this command as well. And then when you enter, it will report that what you have used. Okay, like I mean, for myself, box, I'm using this semaphore, which in fact I don't create. Some program that I run natively, okay, it use or make use of the low level synchronization to call semaphore. Okay, and but also, by the way, wheel, WHEEL, man, I have not seen this word for a long time. When I was a graduate student, I used to be system staff, okay, or system admin that manage data center. So we have a parallel machine and different other machine. And wheel also is one of the group name that belong to the root or the system admin. Okay, I don't know why it's called wheel, but anyhow, that's what I'm talking about, the Linux or Unix type of synchronization. And then p-thread, we already talked about p-thread in this in the previous chapters. Okay, quickly on Windows XP synchronization. Okay, in Windows XP, or generally speaking, in Windows system, it uses interrupt mask to protect a global resource access for unit processor, but it uses spin lock on multiprocessor. You can remember spin lock or BC kind of spinning. I mean, you have while loop, because in that case, I think it's quick in terms of implementation, and then assuming that you're gonna use this synchronization briefly. Okay, so therefore spin lock is not that bad. When it talk about multiprocessor, I think including multi-core as well. Okay, and also as well on Windows system, it used provide this patch object. Okay, in order to act as mutex or semaphore. Okay, and then the dispatch object may also use to provide event, which is the event notification mechanism, in order to be used like condition variable, as we discussed in pthread. So briefly on Windows XP synchronization. Okay, then the Linux, as I told you, we have semaphore and spin lock, and I think it used to disable interrupt in order to implement a short critical section. Okay, and last but not least, in terms of pthread synchronization, we have talked about pthread mutex lock and unlock, and give you example on conditional variable. I believe that the example code, if you download and play with it, P3, P2 and P3, in fact P2, P3, P4, they all use mutex lock and unlock. And then P4 example, it incorporate a conditional variable where we have two process or two thread that trying to update count from 0 to 11, and then define by thread number 1 do 0 to 3, and then P2 do the rest until I believe 9 if I'm not mistaken, and then P0 or thread 0 continue on the rest. Okay, some of the implementation of this synchronization in pthread, because again pthread is a standard API, which is operating system that agnostic or independent. Okay, that means pthread may be implemented in various systems because it IEEE standard. Okay, so therefore there are different implementation or extension for non-portable extension, include using read and write locks, and then spin lock as well. Okay, so that is a summary of synchronization, which is lecture 6 or chapter 6. Okay, instead of continue on into chapter 7, which is deadlock, let me give you a synopsis or a general idea of the new homework. Okay, so let me switch to our Moodle website, and you're gonna see what I have upload. Okay, so now let me see, this is website. As you see that let me see now, today is, I don't know why it's always when it in between two sections, it's lag behind one day. My Moodle said that 14 to 20 is current. In fact, today is 21st. Okay, so if we click 21st here, then we have a new programming assignment which called Dining Philosopher Problem. So you can download, and then original due date is April the 30th. Okay, but this morning after I review, I mean the reminder again, I have changed my mind. Okay, because otherwise I would feel that you're gonna get a lot of pressure there. 25th, I'm planning to have, I'm debating whether I should have another a quiz or not. I should, because that the quiz will help to validate your study. He also politely force you to listen to this lecture. I know that most of you guys, at least more than half from the class, you guys, get on during this live broadcast. But a few of you guys, if I don't ask homework or quiz, some of you guys may not be motivated in order to follow the class or listening to uh, this lecture. Okay, so therefore the quiz, or often quiz would be a tool to help you, help me. Okay, meaning that help you to force yourself. Not you who listening to me. Okay, but then there are someone who may not wake up. This is the right time. Okay, and then listening. So quiz would help to force you to listen and then to do the quiz. So quizzes also help me to see whether you learn effectively or not and understand. Okay, but anyhow, I would announce on Thursday whether we can have quiz or not. Okay, but also you have multiple due date or deadline for this coming week, which means Friday you're supposed to upload 5 references of your term presentation. Okay, and then Tuesday you should have your PowerPoint complete and ready to be present, via Zoom session. Okay, and then also I need you to start practicing in terms of programming experience, and then P-Thread would allow you to continue, improve your skill set in terms of C programming language, as well as explore yourself into multi-threading or parallel programming. Okay, so in that case, originally I thought gonna have the due date on April 30th, but then I'll push it further. I think the new due date is gonna be May the 5th. Okay, which means the next Tuesday after April 30th here. Okay, so if you click here, you're gonna see the let's see. Okay, the problem described in detail in this PDF or PowerPoint PDF. Okay, which in general, okay, let me switch to, I already make summary. Okay, but you can read through this one. Okay, but in summary, it's gonna be in this PowerPoint that I would upload to you. Okay, where is it? Okay, project 2. Okay, programming number 2 is let me change the date. Instead of April 30th, it's gonna be May 5th, I believe. Let me just quickly check on my calendar. Yes, the 30th is, yes. So I give you a few extra days to work on this. You should have enough time. Okay, so let's talk about this. Okay, it's about dining philosopher in P-Thread. Okay, and the due date is May 5th. The picture is the same as I show you on the discussion on synchronization, as well as the deadlock. Okay, so you have a number of philosophers. In this picture is 5, and each of them share left and right chopstick. So you have 5 chopsticks that laid down around the table as such. Okay, now the requirement is that you have to write a P-thread programs. Okay, that create number of thread defined such as, okay, let me show you this, the pen. N, it show number of eating, okay, before exit. M is number of philosophers. Okay, so if you write a program, let's say that if your program call a.out, or maybe you rename as dfill, and then you pass 2 parameter 2 and 3. 2 meaning number of eating, eat, and then 3 is number of philosophers. Okay, so this could be as many number. I would say the suggestion limit up to 32 philosophers. Okay, you can create 128. Okay, so that means when you implement this, if you dynamically create number of philosophers, your code would be a little more complex. Okay, so in that case, you can predefine that the number of philosophers can be up to 32. So in that case, you would check the second argument here. If the second argument is numeric number or integer, but it must be greater than 0 or less than or equal to 32. Okay, If it's so, then you create number of thread based on provided number as second parameter here. And then number of each is for you to track within the logic of philosopher, okay? So maybe initialize, each of philosopher may have local variable called uh, count, or eating count, okay, which is its own. It does not have to be the global variable, because that count is just for each of those philosophers. So I think you have to make sure that you pass this parameter so that the philosopher would know that how many times it's supposed to eat, okay? Then you make sure that your program has no deadlock, okay? So how do you do this, okay? If you are C programmer, okay, first you have to handle from command line, okay? In order to pass parameter from command line, okay, to your C program. In C language, we have mechanism called argc and argv, okay? So, and also we'll talk about those later on. But beside that, when we say there's no deadlock, one suggestion or one solution you can implement is called asymmetric solution to prevent deadlock, okay? When we define asymmetric solution, so in your the function that you implement dining philosopher that gonna eat and wait, okay, you need to pass the index of each philosopher, okay, where you use that index to determine whether it's odd or even number, okay? So if index say 1, okay, it's odd number. If it's 2, then even number, right? So I think there's some logic that you can do modular arithmetic and then figure out whether it's odd or even number, okay? And then if it's odd number, so you check if it's odd, then you may also implement your own function called odd or evens, okay, and return true or false. If it's odd, then first pick the left chopstick, then pick the right one, okay? Otherwise, if it's even number, then first pick the right opposite way and then pick the left, okay? You guys start having some ideas how to implement this, okay? Also, the main logic that I would suggest you, okay? First, read the command line input as a string, because I mean you can use argc and argv. Argc is define number of arguments from command line that you can pass from command line and connect to your C program. And then you can use argc to retrieve the parameter in argv, which is an array of arguments, okay? Parse argv for each of them. So you're supposed to have 2 parameters, right? 2 command line argument. The first one would be number of each. Second one would be number of philosopher. It's gonna come in as a string, okay? So or ASCII. So then you have to convert from ASCII to integer using a function called a to I. Are you guys with me so far? Okay. Then after that, after you get number of philosopher, then you would use number of philosopher to drive or create a number of chopstick mutex. So you have to put in the loop, okay, and then drive by I from I equal to 0, I less than the second argument, which is number of philosopher, and then we initialize mutex variable before you can enter, because in your logic in dining philosopher, you will have to use a mutex lock and unlock on this chopstick, okay? And then after the you create number of thread by using for loop, okay? Then the master thread will use for loop, okay, to call the p-thread underscore join in order to wait for all children thread, which is dining philosopher code that you assign to work on, okay, until they're complete before the master fall down and finish your program. So this is a general logic of the program, okay? You guys have any question or anything you want me to show you more? Why not? So I just do the screen dump on the code that almost complete. I can't upload this code for you because Otherwise, it will be too easy. So let's take a look at sample code here. This is the actual code that it probably work. My code is called din.c. Quickly, okay. I think to write pthread program, I mean, you can start off by copying maybe perhaps, let's say pt3.c. Copy pt3.c and then copy to the new name called din.c, okay, and then modify it, okay, modify it, okay. So in this case, you first declare a function. This is probably can be DFIL or dining philosophers, okay, dining philosopher function that you can assign to pthread underscore create, okay, and then you define any variable that this is similar to DFIL. This is the second argument, number of thread here, and then time to eat, number of, okay, as I told you. You can limit number of total, the maximum number of philosophers up to 32. So in that case, it will simplify your code instead of dynamically create this mutex, okay, variable, okay. Then you can just say, okay, I pre-declare the max would be 132 or 128 or 32. In this case, I assume that the maximum number of philosophers is 32, okay, and then you also have some sort of a utility variable to start or to indicate the start and stop, okay. Now coming to your main program, okay. In order to take argument from command line, okay, normally your main just have nothing or void, okay, but also C language provide you an option that you can pass command line argument, where the first argument is number of argument, and then the second argument is an array of character string or string characters, okay, character string, okay, which is in this case we want to make sure that we're gonna take 2 arguments, so the total number of arguments must be less than 3, right? Less than or equal to 3, because it's gonna be the program and then 2 arguments. So the maximum number of 3, okay. If it's not so, then you will say that, okay, if it's not equal to 3, then you say invalid number of argument and then exit. You don't want to do anything, okay. Otherwise, all you have to do, you're gonna take the first argument. So the arg0 is the program name, either a.out, or if you name this program to be DFIL, gonna be DFIL, okay. And then the first argument, which is this one, okay, is number of it, okay. So if you call a.out, two and then 3, 2 will be number of eating, and then this one is arg1, this is arg0, argv0, argv1, and argv2, okay. So in that case, you call a2i. A2i is a utility from this standard library that allow you to convert, because argv, as you see that this is a character string, so you have to convert from ASCII. A is stand for ASCII, T in for integer, ASCII to integer, okay. That you will convert string 2 into number 2, because otherwise your program would not know. And then because you declared time to eat, number of time to eat is integer, so it requires a match data type, which is integer. Make sense? Okay, now let me show you one more and then I'll let you go. And I think next time, if you need more help, I can go into more details, okay. So let me show you, and then, you know, after you check the argument, and then you do arg2, okay, arg1 and arg2, which is, this is number of eat, and then this is number of philosopher, okay. You do the same thing by convert from ASCII to integer, and then you have number of thread or number of philosophers, okay. Also, you will predefine, as I show you on the previous screen, that we show you the the maximum number of chopsticks should be matched to the maximum number of philosophers. So we predefine that the max would be equal to 32. So in fact, you can check the logic here. Before you proceed, you can put error checking here to say that the arc number of threads should less than 32. Okay, or equal to 32. Otherwise, you should not do anything, because otherwise your program would not work. If someone say defill defill 5 and 60, the second argument would be 60, right? Which is larger than this, so it does not work. So in this case, you need to check this against the maximum number that your system can support, okay? If it's larger than 32, exit. Don't do anything, otherwise proceed, okay? And then after that, then you will create number of threads based upon this number of threads that you take from command line, okay? And then time eaten, okay? You also have to track for each of the philosopher, okay? You need to track number of eaten, okay? And then after that, then you would go and start initialize the mutex, okay? That you want to perform for chopstick, okay? So in that case, you do for loop, okay? For I from 0, I less than number of thread, I plus plus, and then do pthread mutex init with each of chopstick with this index I, okay? And then we don't care about the second parameter, then we'll just put null there. After that, you get ready to create number of thread. So in that case, you do pthread underscore create and then do pthread join. So I'm gonna end up, I think this should give you enough idea to start your assignment, okay? And you can see that pthread underscore create, okay, called thread function, which you have to define whatever this dining philosopher logic or each of philosophers supposed to do. Maybe the first version that you should come up with in the thread function, or it does just, you just print f or prompt out to say that I'm philosopher 1 or 2 before you start adding. Don't try to write everything in one shot. It's going to be too complex, okay? So why don't we do this? I think we go over the time already. Just go ahead and then use this idea. I will upload this PowerPoint on the Moodle website. In fact, I have a little more from you. It's just your bonus idea, I mean, to start. And when we come back next time, if you guys want, I can start with this again and then maybe try to run the program and show you. All right, guys. So otherwise, if you guys have any question, feel free to just type in this live chat, or you can send me email. Otherwise, I mean, if you want to talk to me, can be anytime. It doesn't have to be during my office hour. Just send me email. Look at the Zoom URL that I post from last week. We still can use that one, the same one. So we don't have to use the new one all the time. So just send me email, give me a few hours appointment lead time, so that we can say which time we want to get on together, and then we can talk, because I don't want to just wait there. And last time I was on Sin 1:30, and then I just keep waiting until 3 o'clock, and then I would just keep watching different thing, and then suddenly I heard one guy say, "Hey, Dr. Box." I said, what is that thing beside the YouTube thing that I'm watching? And then I was so happy that one guy just tried to reach me, and we talk in length and explain in detail. But otherwise, guys, start working on your term presentation, this assignment that I have given to you, and review the material. And I'm so proud of you. I think most of you are already on, and I think some of you guys already signed up. You might have another class to go. So otherwise, hanging in there. I think we are doing okay, and let's work together and be safe, okay? All right, guys. So I'll see you this coming Thursday. All right, okay. Have a great day. Bye.